Chapter 15 is our third chapter on equilibrium, and what we're going to look at in this chapter is more acid and base reactions, looking at something called buffers, looking at what's called the common ion effect, and solubility equilibria. We're going to start out by just kind of reviewing acids and bases and what happens when we put in an ion that's common in the acid from another source. We're going to start out by looking at acetic acid. Remember, this is our way of abbreviating acetic acid, and it's going to dissociate and give us some hydrogen ions and some acetate ions. We're given the Ka of 1.8 times 10 to the negative 5. If we start with a 1.5 molar solution of acetic acid, if we go through the equilibrium process, what we find is we have a hydrogen ion concentration at equilibrium of 5.2 times 10 to the negative 3 molar, and that gives us a pH of our solution of 2.28. Now, if we take this acidic solution that it's in equilibrium and we add 1.2 molar solution of sodium acetate to it, our acetate ion is the common ion because it's present in both sodium acetate and it's present in acetic acid. So now we're going to take a look at, we're starting with 1.5 molar acetic acid again. It's approximately that, even at equilibrium. We're going to say that we have no hydrogen ion yet, and we're going to add 1.2 molar sodium acetate to it. So we're starting over initial conditions. Because these are our initial conditions, for equilibrium it's going to shift to the right because we need hydrogen ion. So for our delta X, we have minus X here, and X here. So at equilibrium, we have 1.5 minus X for our acid concentration, X for our hydrogen ion concentration, and 1.2 plus X for our acetate ion concentration. So now if we try and find the hydrogen ion concentration and then the pH, it'll look like this. Same deal, we're going to take the Ka of 1.8 times 10 to the negative 5. In our numerator we have X, and we have 1.2 plus X, because that's for the acetate ion. In the denominator we have 1.5 minus X. With the X's in the numerator and the denominator, we have to figure out, can we cancel them or not? Our exponent in the K value is to the negative 5, so I can cancel out the X in the denominator. Can cancel out the X added to 1.2 molar, and so now I can solve my equilibrium, and I get a concentration of hydrogen ions equal to 2.25 times 10 to the negative 5. That would be molar. Now this concentration is a lot smaller than our concentration of hydrogen ions with just plain acetic acid. That was to the negative 3, so it's over 100 times smaller. This is to the negative 5. So the pH for this solution is not going to be as acidic. If we solve for pH, we're going to find the pH is 4.65. So when I have a weak acid and the negative ion from its salt, or when I have a weak base plus the positive ion from its salt, I have what's called a buffer. The nice thing about a buffer, the reason I would want one, is a buffer is a solution that resists dramatic pH change. Remember, when I'm changing pH, anytime I change the number in the ones column, I'm changing a power of 10. So if I change numbers in the tenths or the hundredths place, I'm not changing the concentration a whole lot. I may be changing it a bit. So if we take a look at this example, we have a 0.5 molar solution of acetic acid, and the pH of that solution is 2.52. Hydrogen ion concentration is 3 times 10 to the negative 3. Now if I go through the equilibrium, what I find is at equilibrium, if I started with 0.5 molar acetic acid at equilibrium, that concentration of acetic acid drops to 0.497 molar, because 0.003 molar of it is now hydrogen ions and acetate ion. What I'm going to do now with my acetic acid solution at equilibrium is I'm going to add 0.2 molar sodium hydroxide to the solution and see what happens. So if I'm going to add 0.2 molar of a base, that's going to decrease my acid concentration. So it's going to be 0.497 minus 0.2 molar. I'm going to increase my hydrogen ion concentration because I'm driving the reaction to the right. So that's going to be X. And for each acetic acid molecule that I rip off a hydrogen, I generate an acetate ion, and so my concentration of acetate ion is going to be 0.003 molar, which is what I started with, plus the 0.2 molar that I add from the sodium hydroxide. So if I want to find what is my hydrogen ion concentration now, I'm going to put it into my equilibrium expression. 1.8 times 10 to the negative 5 equals X in the numerator times 0.203, if I add those two together, divided by 0.297. And what I find for X, which is my hydrogen ion concentration, is I get X of 2.63 times 10 to the negative 5. And if I solve for pH, I will find that the pH is 4.58. So I started with a pH of 2.52. I add 0.2 molar base, and I end up with a pH of 4.58. So that's a relatively large change in pH. It's two pH numbers. Now I want to do the same thing. I want to add another 0.2 molar sodium hydroxide to my solution that I've already made. And so now I'm going to start with concentration of 0.297 molar acetic acid and roughly 0 molar hydrogen ion and 0.203 molar of acetate ion, so that's roughly initial concentration. So at equilibrium, I'm going to have 0.297 minus 0.2 X here and 0.203 plus another 0.2 molar acetate ion being liberated. So to find my hydrogen ion concentration, again the same thing, put it into my K expression and solve for X. When I solve this, I get an X, which again is my hydrogen ion concentration, of 4.33 times 10 to the negative 6. It's molar, and my pH for this solution is 5.36. So this time I doubled the amount of sodium hydroxide that was in the solution, but the pH only changed less than a pH point. So it's a significantly smaller pH change than when I first threw in my sodium hydroxide. And so that's the advantage of a buffer, is it slows down the change of a pH. Now, for comparison, if I wanted to start with water and I had 0.2 molar sodium hydroxide, that's just the concentration of hydroxide ions being 0.2 molar. And so if I do the pOH, I'm going to end up finding from that I have a pH of 13.3. If I look at adding 0.4 molar to water, so my hydroxide ion concentration now is 0.4 molar. I'm going to use the hydroxide ion to find the pOH. I get a pH of 13.6. So in both cases, going from water to adding base, I get a huge pH change from 7 to 13. So a pH jump of 6 pH points as opposed to 2 or less than 1. So again, buffers significantly decrease the change in pH when I'm adding them to a solution. And that can be an advantage, and it's one of the things that biological systems have developed to maintain a fairly constant pH within the living organism.